Hello, everyone, and welcome to my presentation um, about strategies for handling large-scale AI in distributed environments. My name is Avishai Saban, and I'm very excited to be here today. A little bit about myself. I've been working in the field of AI and big data for more than 2 years, and I've been excited journey so far. In the past, I was mainly focusing on software development and cloud native solution. And at Converge, I work with the clients to design, productize, and implement AI solutions that help them to achieve their business goals. And today, we're going to discuss why distribute and the pain points in deep learning, why Kubernetes, and how to distribute it. And how does parallel work? How does data parallelism work? We're going to talk about scalable machine learning frameworks and platform like Pytorch, Kubeflow, and Pytorch with Ray. And we wrap up with a quick demo of running Ray with Converge platform. So with a little bit of motivation, I want to start the question, why do you think distributed computing is becoming more and more important? And as you can see from this diagram, this is a couple of lines superimposed on a plot from an OpenAI blog post where they talk about the amount of compute required to achieve certain state of the art in machine learning. So everything from AlexNet back in the days to AlphaGo, and if you know, you could actually add GPT-3, Stable Diffusion, and some of the newer models to this plot. Actually, this plot shows the same trend. And basically, if you look at the amount of compute required to achieve this kind of result in machine learning, it's going way faster than what you can do with a single chip. So even Moore's law has continued at the same pace, slowing down, doubling every 18 months or so. Even if that had continued, there's still just tremendous gap in what you can do with a single chip and what you need to do in order to do a machine learning training. And the similar story is true about with serving and other kinds of data processing and other kinds of workloads. And so given this trend, there's really no choice but distribute this application. And of course, accelerators like GPUs, they all help. But fundamentally, they govern by the same growth as Moore's law, and they have higher y-intercept, but they don't fully close the gap. So no matter how you slice and dice it, distributed computing is just here to stay. So the problem, so what are the problems we've seen today in deep learning? One of the major challenges is dealing with large amount of data and complex computation. And so training can be a significant amount of time, especially can take amount of time, especially if you with large data sets and complex models. Additionally, there may be limitation on the amount of data that can fit on a single node requiring distributed computing. And furthermore, with the increasing size and complexity of deep learning model, is becoming more common for models to be large to be fit on a single device. So these challenges require innovation solutions such as distributed computing framework and specialized hardware to improve the training speed and accommodate large models. So why Kubernetes? Kubernetes is the most popular example. And when it comes to deploying and managing machine learning workloads, Kubernetes is a powerful platform that addresses those challenges. Kubernetes provide us full tolerance and high availability for your application running on, and this allow you to focus on building, deploying your application while Kubernetes handle the complexity of running them at scale. And one of the key reasons Kubernetes success, it's the open source nature, which means that anyone can contribute to its development and use it for free. So one of the main key benefits, it's provide the declarative style of running software components. It's provide the abstraction layer for hardware resource, and also provide an API so you can interact with it. Okay, so when it comes to distributing machine learning workloads, there are two primary approaches, which is the data parallelism and model parallelism. So here is an overview of each approach. So in data parallelism, the training data is partitioned across multiple devices or processes, with each device or process processing a separate slice of the data. So during the training, each device or process computes the guardians based on a slice of the data, and these guardians are then the average across all devices or process to obtain a single guardian vector. And the guardian vector is then used to update the model parameters. And by parallelizing the computation across multiple devices or process, data parallelism allows for faster training and the ability to work with the larger data sets. And additionally, to the batch size used during the training is affected by the number of devices or processes, and is typically divided equally among the devices or processes. In model parallelism, different subnetwork or layers of a deep learning model are placed on different devices and allow for parallel computation of these subnetworks or layer. This can be useful when working with a very large model that cannot fit into the memory or a single device. And in model parallelism, different layer or groups of subsequent layer are run in parallel in a pipeline fashion. This means that the output of one layer is passed directly as the input to the next layer. So each layer is being processed by a separated device. And by breaking up the model in this way, model parallelism allows for faster computation and the ability to work with large models. So actually, both data parallelism and model parallelism have their advantage and disadvantage, and the choice between them depends on specific requirements of the workload. So data parallelism is simpler to implement and can be more efficient when working with large data sets, but it can suffer from communication overhead as the number of workers increase. And model parallelism can be more complex to implement and requires careful design of the model architecture, but it can be more efficient when you're working with large models. So usually the frameworks that support those techniques, the standards in the industry, both for data parallelism and model parallelism, will be TensorFlow and Pytorch. But at this session, we're going to focus on data parallelism with Pytorch. All right, so let's simplify the explanation of the steps that involved in training model using data parallelism. So first of all, we start a multiple worker, and the multiple worker machine are started each with its own CPU or GPU, or a set of GPUs and CPUs. And then we assign each worker, which would be the number, the rank, and each worker has its unique rank or identifying to keep track of its progress during the training. And then we split the data. The training data is split into equal parts and distributed across the worker. And then we start the training. The training process is started on each worker and using a copy of the same model architecture. And then we do the run backwards, pass the model on each worker to compute the guardians of the model and parameters with the respect to the loss function, and guardians eventually synchronizing, and synchronization happens during the backward path in all the reduced fashion, and the guardians computed by each worker, and then the process is stopped, synchronized, and aggregate using the all reduce operation, which combine the guardians and the update of the model weights. So let's see how we can achieve that with Pytorch distributed data parallel. And Pytorch distributed data parallel, in other words, is a DDP. It's a model that implements data parallelism in Pytorch. So to use DDP, you need to start the process with a special torch distributed launch command to assign each worker all the required information, such as the rank number process and the address of the master process. And once the worker are set up, the data is split between them, each worker process, a subset of data samples. And you also need to wrap up the model with distributed data parallel to make sure that the model's guardians are synced across all workers. So during the training process, and this is done by aggregating the guardians from each worker and applying the updates of the model parameters. And finally, it's a common practice to save the model only if the rank is 0. And this is because the first worker, which is the rank 0, is usually responsible for coordinating the training process and gathering the results from other workers. And by saving the model on the first worker, you can ensure that only one copy of the model is saved and avoid conflicts that might arise from multiple workers trying to save the file simultaneously. But deploying Pytorch requires communication between processes, and it can be very challenging. And one of the tools that can help us to address communication challenges is actually a kubeflow. But unfortunately, I don't have enough time today to describe kubeflow, so I'm going to skip it. But I will share my slide right after this session. And I'm going to talk about Ray. And Ray is another interesting growing open source framework I want to talk about, and it is actually my favorite. Ray is a powerful distributed computing framework that allows developers to write parallel and distributed program in pure Python. And one of the key features of Ray is the ability to easily parallelize existing Python function with a minimal code change. So as you can see in the example below, one of the way Ray achieved this is through the use of decorators, such as the ray.remote decorator. And when this decorator is added to the function, it allows the function to be executed remotely on a cluster of machines rather than just on your laptop or local machine. And actually, one of the benefits Ray has is the rich ecosystem, which includes support for a variety of libraries and frameworks commonly used in the data scientists and the data engineers, including TensorFlow, Pytorch, scikit-learn. Also, you can run PySpark if you want. This makes it easy to integrate Ray with existing Python workflow. Okay, so let me let's take a look actually on high-level overview how to use Ray train to implement distributed training with Pytorch. And here are some details, more details. So as you can see, we first of all import the necessary libraries to use Ray train with Pytorch. You need to import both Ray train and Torch library and implement the training function per worker. And this is the function that will be executed each worker during the training. It should take in a dataset shard, the dataset shard, which can be accessed through the session object and perform the necessary training step. And then you start the training using the ray.torch.trainer, ray.torch-trainer. And this class actually allows you to train your Pytorch model on Ray cluster, and you need to provide it with the training function you implement in step 2, along with other configuration options such as the batch size and the number of epoch. And finally, you need to define resource in the scaling config when you start the training process using ray.torch-trainer, and you can specify how many resources you want to allocate it for training. And this can be done using scaling configuration, which specify the number of nodes, GPU, CPU, and other resources that should be allocated for training. So the solution overview with Ray. Ray is a Python native solution for distributed computing and machine learning. Ray jobs can be used for asynchronous execution of tasks, and Ray provides a monitoring UI for tracking the progress of jobs and performance metrics. But yeah, the challenges with Ray is, it could be a cluster installation, can be challenging with Ray and require manual configuration use of the third-party tools. And Ray can be deployed on Kubernetes, but require installation of Ray operator. So here in Converge can definitely help data scientists who are new to Kubernetes or may not have experience deploying and running model experiments training on Kubernetes. And Converge, which is part of Intel company, is an AI operating system that simplify the entire machine learning workflow from a data preparation to a model deployment. It provides user-friendly interface and abstracts away all the complexity of Kubernetes and resource management, and allowing data scientists to focus on their core work of design, training, and deploying machine learning models. And the platform also provides feature like version control, automated hyperparameter tuning, easy builder pipeline, and model serving, and make it easier to manage the entire machine lifecycle without relying on IT teams and DevOps. And before the demo, I would like to show you how to run Pytorch experiments using Converge. And there are two ways to do it, using the Converge SDK or using the Converge UI. Or to do this through the UI, you can create a new experiment and upload your train.py script, for example. And we actually take the script and we wrap the command with Pytorch distributed and set up communication between workers. All right, so let's start with the demo and show you how we can run our Ray in a very easy way with Converge platform. All right, so if I go to one of my projects and upload, actually I already created a project. So if I go into my project, which is, I call it Ray, I already upload my files into file section, but you can also integrate it, connect that with your Git repo. So everything, we kept all the history commit for you as a version control. And before I'm going to run this torch fashion MNIST example, I'm going to, first of all, create a Ray cluster template. So all I need to do is going to compute, and I'm going to have my resource here. I have a resource from Azure, for example, and my templates are here. And all I need to do is just creating a template for me that and the templates help me to abstract away the hardware. And here, as you can see, Converge provides a bunch of technologies for distributed computation from OpenAPI, Pytorch distributed, Spark, Ray, and Modern. I'm going to choose Ray, and then I'm going to give it a name, Ray cluster. And here I'm going to specify how many CPU I want. So I'm going with 4 CPU and 8 GB of RAM. And for the worker, I'm going to add 2 and 4 CPU, 8 memory, and 1 GPU. And once I save this, I have this template, and I'm going to allocate my job using this template. So I'm go back into my Ray project, and I'm going to go into my workspace and spin up a workspace. So I can choose between Jupyter, RStudio, VS Code, and can give it a title. I'm going to choose my template, which is the Ray cluster. And then I'm going to import my data set, whether if I have a data set. And I'm going to bring my Ray container, which is the latest container from Ray. And I'm going to start a workspace. And so I already have my Ray workspace. And as you can see, I'm going to open my Jupyter notebook. And let's wait. Okay, so here I have my terminal, and I'm going to switch into my bash, and I'm going to just write my Python torch. I'm going to execute my Python torch, and the code looks like that. As you can see, I have my array and torch, and I'm going to execute my Python code right now. And let's wait. Yeah, and as you can see, it started a local Ray instance. And all I need to do is just going to the nice icon over here on the right. This is the Ray UI. And I'm going to see all of my jobs. And this is the execution of distributing Ray jobs. As you can see, I have my master and 2 of my worker. And this is, we can see that at runtime running and executed as a distributed fashion way. All right, so just in summary, if you are a data scientist who wants to leverage the power of Kubernetes, but lack of the experience to do so, Converge is a great solution that can help you to accelerate your machine learning project and achieve better results. So I invite you to join us and see for yourself what MetaCloud is all about, which is our SaaS version. And it's a great opportunity for anyone interested in building and deploying AI applications. User can start exploring the platform and building their own AI project without upfront cost or commitment. So you can start with 4 CPU and 8 GB of RAM for free. And in addition to that resource, the platform also offers Intel Cloud resource, which include access to the most and finest and popular CPUs like Sapphire Rapids. And this is make it possible to build and train complex model with the double price performance and cost compared to other cloud providers. Thank you so much.